On the discussion for the complex rupture, I think it was Brad or Julian had said the hypocenter, we should have a wider range of hypocenter distributions. I forget, one of you said that. For this case, if any of you who've run dynamic rupture models, do you ever get a case where the splay fault initiation actually starts sort of a little downstrike and then comes back, or does it always start at the end? Because we're assuming it starts at the junction. I don't know, Ruth, if you are still online, did you guys ever get one that started in the middle or jumpy?
I think for landers, I think Jim Rice's group looked at that. They were trying to figure out if you could get things, so that would be like a back bridges.
Right.
Yeah, so they did their theoretical modeling or dynamic rupture modeling. They couldn't quite get it to go that way, and then they instead said it must have been a step over jump. But I'm not sure. So those guys explored the parameter space really well, and I'm not sure if there are other cases that have done that, but there might be.
Brad?
I can't remember. Maybe it was our step over case. We nucleated past the end where the overlap was, or maybe it was our last branching case. We've done so many cases I forget. Ruth, maybe you can remind me. We had one case where I think it was the branch, the splay case, where the second time we ran it, I think we ended up running maybe super shear and it jumped past the intersection. But it's one of those things that it depended on the parameters.
Yeah. I'll have to. You probably remember better than I do, but we can definitely go back and check that.
This is Doug Drager. There's also a case that David Oglesby did studying Denali in which there was jumping to Tachunda, which came about from a favorable orientation with respect to the regional stress field.
I mean,
Doug and prior co-authors on that, yeah.
Julian again. I in the models I did with the double bend, I did get, particularly in cases where the bending point itself was clamped, but the overall segment orientation, the overall linking, bend segment was still favorable. I would get jumps that were more towards the interior, more into the middle of that segment as well. It wasn't necessarily right at the junction because it was clamped and unfavorable, so you can sometimes get that.
Just to reinforce that point, in compressional arrangements, there's a tendency. Yeah, in compressional branching or step overs, there's a tendency to branch forward, and that's just because of the shape of the Coulomb stress pattern ahead of a rupture. But just to confirm what Julian just said, we saw that a lot in step over calculations.
I'm not sure I got an answer. No, I think you said in a restraining bend it will tend to start at the intersection. Is that right?
No, further
It will
down.
start with a jump. Okay, so we should be, if we're doing this kinematically, we should be putting some hypocenters of the splay not at the intersection, but pushing them along strike.
Make sure that that's consistent with what Julian has.
But you have to use the microphone. Just say that again.
I just wanted to say, let's ask Julian if that's consistent with his more recent experience.
Yeah, that is consistent. I mean, the most recent stuff I've been doing has all been extensional because it's the San Jacinto, but with the most recent compressional stuff I did, whether it's bends, double bends, or step overs, I definitely still see that forward jumping with the compressional cases, whereas the extensional ones, in a step over, it would jump right to the point immediately aligned with the end, or in the extensional bends, it would just turn the corner, but no, compressional definitely still jumps ahead.
Yes,
Yeah, I have a question about how you generate the slip distribution, or when you use a rupture generator. Can you explain again how do you produce the kinematic model for the smaller branches? We know that the input parameter for those is the magnitude, I guess.
Mm-hmm.
So how you distinguish between the fact that they are smaller folds and
So my inputs, I have the magnitude of the smaller, of the splay. I specify the location of the hypocenter because that's fixed. And then we're running 32 randomizations or realizations of the slip and the velocity. That's 30 random realizations. And the geometry of this source is specified in the inputs.
So the magnitude for each subsegment or segment is different?
Yes, that's correct. This was run as 4 different simulations. So the platform doesn't know that I'm making splay faults.
Okay, but you said that you maintain the seismic moment. So you scale up then the slip on those little segments?
Not for this, not for what I showed here. So for what I showed here, the magnitude for this segment was based on Leonard scaling of the length and the down dip width.
Okay.
And that's true for each one of these cases. And then they were combined in a post-processing, to produce the splay. So the moment is lower than what the moment would have been if I had computed the total moment of the main fault plus splay and then partitioned it before running the scenario. That's the other way I could have done it.
So which way would you think, how would you recommend this be done?
Well, I think to be consistent, we need to assume that even though the faults, the fault geometry is smaller, the effect, we should maintain that use the same magnitude for all segments. Even though the geometry is different, the magnitude should be the same, and because that will affect the kinematics of everything in that segment.
Rob
That's what
wants
I
also
just-
to add
So
some.
can I just say something because I'm a little confused by this? So if my magnitude on the Haas degree is 7.2, are you suggesting I run a magnitude 7.2 splay?
Well, there is a maybe Rob will probably if he's there. Some of the parameters that we are assigning to the slip model correlate with magnitude also.
Okay.
So besides the scaling that you may do to fit the seismic moment, there are other things that need to be taken care of.
Rob, are you on there?
Yeah, this is Rob. Can you hear me?
Yes.
Okay, yeah, so these are some important points that Arvin is raising. And it is difficult to try, we're using the platform to do something that it really isn't set up to do yet. So as Katie explained, the way that these simulations have been done is probably not the way that we really want to do it. I think what we should do is scale the magnitude for each of the individual segments such that the average slip on that segment is the same as the average slip for the total rupture given the total target magnitude. And so what that will mean is that each of the individual segments, if you looked at them as individual earthquakes, they will actually be high static stress drop events. They're going to have more slip than average for that fault period.
But Rob, can I interrupt for 1 second, just so I understand? If I have a splay that's running, the main fault coming and the splay coming off, in that overlap part, you would have twice the slip. Is that right, if I added them up?
Well, yeah, that's an even, yes, in the way that I'm describing doing this with the current setup, yes.
Okay.
Yeah, and I don't know what's right for that situation. That's something that maybe
But that's where
ruptures can give us some guidance on. But trying to think through this with the current set of codes and the current parameterization that we have available on the platform, what is the best way to do this? My thinking is, in the end, we're going to sum up the response from 3, 4, 5 segments, and we want it to be a magnitude 7.3 or something like that. okay, how do we then partition the slip or the parameterization on those individual segments to get that? And I think that the most straightforward way with the current setup on the platform is to make sure that each individual segment has an average slip that would be equal to the overall average slip for the full set of ruptures.
But why is that? I guess I would like to follow on, let's say, follow your advice of let's go to the dynamic ruptures and see what they show. Because on any of those splay fault ruptures, Ruth, I don't know, do you see what's the slip on the splay compared to the slip on the main part for the restraining bends?
The restraining bed, I'm not sure if Julian has any in his slides, but the restraining bed had almost no slip for the benchmark simulations that we ran. Also, the angle's pretty narrow and the faults are pretty close together, and you'd expect this, and we think that stress shadowing works, then you think there would be a shadowing effect. And I think everyone who's done these types of simulations has seen that in their work. As soon as the faults get farther apart, I'm sure that Julian's also seen it in his talk, and he could probably talk about it right now. But as soon as the faults get anywhere near to each other, then there's a trade-off. There should be a trade-off because there's a moment balance that you need to do.
Julian here. Is this on? Can you hear me? Okay. With the back branching, I mean, well, I haven't done any branches in that sense, but I've had some with some of the step over ones where I get a jump. I will still get a bilateral rupture after the jump, but to the interior of the step over, like towards the direction of the fault that just ruptured, it's definitely less energetic going in the backwards direction. I mean, so there even if there is still a slip rate or a ground motion signature, it's a much less energetic slip rate. It's a much weaker ground motion signature going back towards the area that would have been shadowed by the primary rupture.
So Rob, instead of, I think, grabbing an approach right now, how about we look at some of these dynamic ruptures and then sit down and try to find a set of rules we can say make sense or alternatives for how we stick it into the kinematic run. Is that?
Oh, well, yeah, that's fun. I think exploring or using that as guidance is definitely useful. It may be a little bit difficult to parameterize, again, with the current set of codes on the platform. If, for example, if one of our rules is, okay, when two faults start to come together, we want, half the slip to be on one and half on the other. That is going to be a little difficult with the current code set.
Okay, go ahead.
Do we have some information from geology, from mapping ruptures? Do we have any information from mapping ruptures of splays on the surface, what the slip looks like on the splay versus the main trace that we could use for this?
There's not too many geologists in the room.
Well, you look like you're leaving.
So there are a lot of data on this from mapping of surface ruptures, and I think I'm not sure to what degree you guys have already looked at the data set, but where you do have splay faults, a lot of them have nucleated on the splay fault and ruptured onto the main fault. And I think you have far fewer cases where you have rupture on a primary fault that ruptures onto a splay fault, except for, unless you consider something like the Ismet rupture, which wasn't really a splay fault, it was really a fault at an angle, but it's part of the primary fault zone. So I think part of it depends on the way you define things. But there are a lot of information out there.
Okay. Chris Wills.
Tom, I can't remember the reference, but I believe there is empirical studies where they show this. When you have rupture on a splay fault or on a branch fault, it tends to have more displacement than if that fault had ruptured by itself. And so what they're talking about in these models is they model those branch faults as independent magnitudes appropriate for that smaller fault. But if you have more displacement than you would typically have for that smaller fault when it ruptures together, then maybe these magnitudes on the splay needs to be scaled up for the displacement on the whole fault.
Steve? I think this is all we have time for, right? All right,
Yeah,
you're last.
Just to follow up on Chris's comment, Glenn Biazzi's presentation at our workshop 2 presented some of those data. So you can look at his presentation from the SSC workshop 2, and he shows them on displacement length plots and shows that they deviate from the main Wilson-Coppersmith data set.
Okay. So this is going to conclude our Splay fault session, but modelers, please think about this because we're going to ask for some guidance in the next SCEC meetings, SCEC calls. We'll be talking about this.
This is back to how thick to model the bigger ruptures.
Because we just need to know how to set up the scenarios and get them going. So this is coming back. All right.
Okay. Change of topics to